This video is going to cover biaxial bending. Technically, it's biaxial and unsymmetric bending that can cause effectively biaxial bending, but mainly what we're going to focus on is the fact that we have bending in the X and we have bending in the Y. Now, technically, this can also occur if you have an unsymmetric shape. Say that you have a very glorious looking L shape here, and you've applied just a moment about, say, the x-axis. Technically, though, it's not really applied just about the x-axis, because technically the axis of symmetry for this member where the centroid acts about is at an angle. So if you were to twist this, and it would look something more like an actual L at 90 degrees, then technically your moment that's just going about the x-axis is now going in two different directions. It's now going more effectively like that. So you're going to have both x and y components for your new set of axes. So it is biaxial in the fact that it is going in two different directions at once, an x and a y, or perhaps it would be an x prime and a y prime if you have to rotate your unsymmetric shape. However, to solve for it is the same. If you want to get the total bending in a spot, you simply sum up the x and y pieces. The only thing you have to do is really pay attention to your signs. Because remember, we're going to do things in terms of tension and compression. And so one of those might be positive while the other one's negative. It just kind of depends on which direction your moment is going in that particular way. So when we are saying to sum, it doesn't just mean add together. It could be add one, subtract one. It could be that they're both positive. They could both be negative. One could be positive, one could be negative. So just make sure you're paying attention to the signs. Other than that, it's effectively just solving the same bending equation, but twice, one for each direction. So we're going to do pretty much the same exact example that we have been doing, except this time, slightly different. This time we have our moment over here going at 40 degrees. 40 degrees. Just thought I'd throw something weird in there. So again, this is the same shape that we had before, so we're going to bring back some similar features that we had before, namely our Y bar, which of course is measured up from the bottom. Should probably keep color-wise consistent with that. So Y bar being measured up from the bottom, we have as 2.38 inches. Now I did get this again from the centroid video, but again I rotated this 90 degrees. So if you want to see how that came about, you can go ahead and give that a watch. X bar is going to be 3 inches. Now at the same time in that centroid and moment of inertia video, I did also calculate moment of inertia about the X and Y axes, but again, because this is 90 degrees, what I called X is actually Y, and what I called Y is X. Long story short, it's 55.1 inches to the fourth for IX, and for IY, it's 81.3 inches to the fourth. So there we're starting off with some basic information. Step number 1, obviously usually to calculate IX and IY. Step number 2, though, we do need to break our moment into its two different directions, and that's going to be moment in the X and moment in the Y. So we do, just to kind of draw this out, have a moment going this way. Again, when you see the double arrows like this, it does mean that that's a rotation, not a force, right? So it is going to be force times distance to give us that bending kind of direction, our moment here. But using triangles, obviously we're going to have X going sideways, and Y is going to be going down. That's how we're going to convert our moment here. And again, that's 40 degrees. So to break it into our X and our Y, we'll start with MX. MX again is going to be going to the right, and MX is going to be, well, we need a value for M first. Let's come over here and say that M is, we'll use the same thing we did last time. How about 24 kip inches? Except this time he is at an angle and not any particular one axis. So now going horizontal, we're saying that M over here is 24 kip inches. So we're going to do 24 kip inches. And then we need to break it up with our trigonometry over here. If I want to do the x direction, I'm going to do cosine for this one of 40 degrees. It's not cosine specifically because it is x, it is cosine because, again, cosine is adjacent over hypotenuse. So again, the adjacent being the direction I want, over the hypotenuse being our 24 kip inches. Another way I like to think about it, especially when it comes to SOHCAHTOA, is that if you are touching the side with your angle, then it's cosine. If you're not touching the side with your angle, then it's sine. So anyway, we're going to get that our moment in the x direction is going to be 18.4 kip inches. And again, it is that direction. What is really going over here to the right with the double arrows actually mean? It means that you stick your thumb on your right hand rule all over again. Stick your right hand thumb going in the direction of those arrows, and the direction that your fingers curl is actually going to be the moment direction. So it's like that. It's going to be coming out from the top. It's going to be going into the bottom. Hopefully that looks decent. Now we've got my. My, again, we're going to be going down, right? So down is the direction for my, and again, it's going to be our 24 kip inches for m, but this time we said sine of 40 degrees. And this time we get our moment to be 15.4 kip inches. So again, what does going down mean? Going down means put your right hand with thumb going down, and the direction that your fingers curl is going to be the moment. So our fingers are going to curl coming out of the right into the left. So hopefully that picture makes a little bit of sense. So there we go. So we have, again, for our bending equation here, our bending equation is m times, we're going to call it c, over I, because again, it depends on which axis you're going. If you're doing the x-axis, then c becomes y, the distance vertically from your point down to the neutral axis, which if you're bending about x, it's the x-axis. If you are doing bending in the y direction, then it is the horizontal distance from your point to the neutral axis being the y-axis. So we have m's, we just solved for those. C is just based on a point, and I, we do have I, we colored those there in kind of a pinky color, so there we go. We do have all of our pieces, at least we can find our pieces, and we want to find what the maximum bending actually is. Now technically we have 4 points, A, B, C, and D there in orange, each in our 4 corners. And you might be thinking originally that you need to solve for all 4 of those points individually and then figure out which one is, of course, the biggest. And by biggest we do mean magnitude, as tension and compression are the positives and negatives, those signs are merely directions. So we could do all 4 of them. I think that would be a bit ridiculous. We can kind of logically break it down. And to logically break it down, effectively we have our shape, just as a rough sketch here. We have our shape, we have our axes, x and y, and let's draw on our moments real quick. So moment in the y direction is coming this way around, and moment in the x direction is coming this way around. So let's figure out for our bendings in the x and y directions whether or not they're going to be positive or negative, because again, to find the total, you simply have to add them together. But if one of them is positive and one of them is negative, they're kind of counteracting each other, so that's not going to give us a magnitude, or the maximum magnitude. If we add 2 positives together, or say subtract one negative from another, then you're going to get a really big number. So we need to find which ones have matching signs. So let's just kind of talk out our directions. We have sigma x's are going to be on both sides of the x-axis here. And based on our bending, let me remind you that if you've got it coming out, this does mean that we have coming out of the face and going into the face is going to create a moment. So again, where we're coming out of, which we're coming out of the top, that's going to be tension, and where we're going into the face, that's going to be compression. So coming out of the top is positive, going into the bottom is negative, same on both sides. Then we shall swap to, I guess, a new fun color, and we can do the same thing for bending about the Y. So sigma Y is going to be on either side of the Y-axis, and it's going to have effectively the exact same concept. So if we are bending this direction, we're going to be coming out of the right, we're going to be going in to the left. So coming out of the right is going to be tension, going into the left is going to be compression. So we have positive on the right, we have negative on the left, positive on the right, negative on the left. Now what we need to do is, did I draw my arrow wrong? No, I did not. Okay. Now what we need to do is actually figure out which ones are going to be positives and which ones are going to be negatives. So positive and positive is going to be a really big number. Negative and negative could also be a really big number. So to remind you of our points, we had A, we had B, we had C, and we had D. So the 2 points that we're going to be looking at is B and D. So let's get started. We'll start with B first. How about that? So for point B, sigma x. Sigma x, we do need mx. Mx is going to be 18.4 kip inches. So we had that written in red, so we'll stick with our colors. 18.4 kip inches. And then the distance to the x-axis from B is going to be, we have the total height of 6, and then we had y bar coming up from the bottom, so perhaps we should do 6 inches minus y bar, and then divided by ix, and as a reminder, ix over here, 55.1 inches to the 4th. Solve for that, and we're going to get 1.21 kips per square inch. Now we'll do the same thing, but for the y direction. So for the y direction, our bending moment in the y direction, we have 15.4 kip inches, and the distance to the y-axis from point B, conveniently this is symmetrical about the y-axis, so it is going to be that x bar distance, which again, let me remind you, was just 3 inches, because symmetrical shape, divided by iy, which is a reminder, iy was 81.3. So 81.3 inches to the 4th. And what we're going to get is 0.57 KSI. So again, for B, you can see it's plus and plus. So the total, should probably make that look nicer, the total bending that we're going to have is plus for X, which was 1.21, and plus for Y, which is 0.57, which is going to get us 1.78 KSI total. This is positive, so in tension. Now we're going to do the same thing for point D. However, for point D, notice they're both negative. So for point D, we're going to start off with bending in the X. And thankfully, we don't have to look very far for this. Moment in the X is again 18.4 kip inches. The distance from point D to the x-axis of bending is simply y bar this time. And then we're going to divide by IX, which is 55.1 inches to the fourth. And what we're going to get is 0.79 KSI. Again, if we do bending in the Y direction, it actually isn't going to be any different because both points B and D are the same distance from Y. We can write it out anyway just to see it. 15.4 kip inches, and the distance, of course, that point D is from the Y-axis is X bar, which again was just 3 inches. So you can see it's the same, especially when you divide by IY, which is 81.3 inches to the fourth. So again, this one was 0.57 KSI. Now for point D, though, it is minus and minus. So when we do the total bending at point D, it's going to be minus 0.79 in the X, minus 0.57 in the Y, and we're going to get 1.36 KSI. However, it is negative, so compression. If we want the maximum, 1.78 is bigger than 1.36. So point B is going to have our maximum bending stress, and point B is going to be 1.78 KSI. So again, you can eliminate a lot of your work just by stopping before doing point A and C. Just look which one's going to give you the maximum. Now, if they did ask you for all sorts of different points, it's not like it's hard. You're just going to continue to add together your sigma x's and your sigma y's to get your total.